Class X deals with multiple reflections. We're going to go back to the beginning of our course and we talked about reflection. And we're going to relate the reflection in a material, say a fairly thin material, where we're going to get interference effects. So reflection and interference, kind of nice to put these two together. And that's going to develop some nice basic physics that has many, many applications, from thin film physics to the Fabry-Perot interferometer. When you have two things that serve as reflecting back and forth, and then if you make these larger, a laser beam has like two reflecting optical elements, and then the lasing material inside. So we'll talk about lasers again today also, and some of the mechanisms behind lasers, and we'll bring back the picture from the first day of class where we had a laser demonstration in class. So that's going to be our topic here, and we're almost finished the semester. I'm going to make the homework assignments short, fairly short, no long calculations like we did in the middle of the course as we get near the end of the semester. And then the next class will be the last one, why. And why we'll have no homework assignment due. I'll do the problems, or I'll do the homework inside the class. So we'll cover that in the class itself. All right, here we go. Chapter X, multiple reflections and lasers, if you want to add. X1, optical path length. Now let's look at the definition of the wave number again. K is 2 pi over lambda. And in general, we have this equation is true, but let's focus on the vacuum and put a little sub O or 0, 2 pi lambda naught, then K over K naught. Since they're inversely related, we just flip these, the lambdas. Speed of light in vacuum is lambda f. Speed of light in some medium is lambda f. So let's put the little o's or the naughts on the vacuum one. Then, these are of the form lambda naught is c over f. Lambda is v over f, put the naught on there. Although we know when you change media that the frequencies stay the same. So if that's the case, the frequencies will stay the same, and that means that when you divide this one by this other one, what will happen is your frequencies will cancel. Let's just go ahead and do that. So this is a c over f naught over, this one here is v over f. So the s would cancel, you get c over v, and that's a cool formula since that's your index of refraction. So you have this nice formula, k naught times n, like this, or k is n times k naught. Just a reminder on the frequencies being the same, if you remember back in the earlier course that we did, earlier chapter, when we looked at refraction and had, say, marching soldiers from grass march into mud, they then turn because they start to go slow here, and these swing around a little bit like the car, swerving and going in the mud. But the main thing here is that if you watch the rows go by, that you have to conserve the people. In other words, if so many go by per minute here, the same amount go by here per minute, since we're not changing the number of people. So in other words, the flow. So your frequency is the same, and what happens is the wavelength gets shorter here compared to up there. And that's the equation. V is lambda F. It's where the velocity and the wavelength change in the same proportion as the frequency stays the same. So this is important because, see, when you have something like the sine of kx minus omega t, or say some general e to the I times kx minus omega t, that when you go a certain distance, then this is going to change your phase. So if you went, say, k times some delta x, and just keep the t constant for now. Say your constant, let's just say t is 0. Just look at the freeze everything. Then this would be the change in the phase. You see, so this would be like a phase change here. Say you could say delta phi. So you can then look at this as representing the phase due to the traveling, where x is the geometric distance traveled, but in terms of the using the formula here, you're going to have k naught in x. So this is the key thing, see, because see, that can be considered your effective, well, it's your optical path length. And in vacuum, it's the same as your geometric length, x, but in glass or some medium where n is not 1, then this is the optical path length. So that's kind of neat to just see that. Sometimes just referred to as OPL, optical path length, is nx. And a lot of times you may see the notation in s, like length, like arc length kind of thing. Okay, let's go on to X2, Stokes, and the interface. Now, we worked with the Fresnel equations way back and looked at the coefficients of reflection and transmission, saying going from air to glass. So let's consider here an incoming ray, and some of it reflects, angles are equal, and some of it refracts. And if this is the amplitude of the wave coming in, then this is A times R, where R is a reflection coefficient, like 1/2, 1/3, or whatever it is. Tells you that basically fraction that's going to apply to the amplitude, and then you need to square it to get the irradiance. And then this would be A times T, the fraction that's transmitted. So basically what we're saying here is if you think from air to glass, you're going to air to glass coming from the top side, then you're going to use R for reflection, that's going to be back into the air, and then T for transmission, that's into the glass. But what Stokes did, rather than look at these complicated formulas that we derived, the Fresnel equations, we're going to do something simpler here. And the trick is to run the rays, reverse everything. So if we reverse everything like this, so that this is, say, an AT, and this is an AR, and this is an A, and then allow for a possible, reflection, because we're coming from here, if you're coming up, you could have a reflection. And then you apply the rule for thinking here, if you're going from air to glass, you have to have another rule, because now you have the case where you got glass to air. So if you go from glass to air, in that case, we're going to use R prime and T prime. So now let's look at what we're going to get here. If you're going from AT, this is here your glass, and if you're going from glass to air, then this here, this is going to pick up, you're going to smack that with a T prime. on the t. So it's actually it's AT t prime, because it's this one, AT, and then you hit a t prime on there to get this. And then here, you would, here for the reflection, this would be AT R prime, since you're reflecting from the glass side. So whatever this is, R prime. But now this one, when this reflects, that's the regular reflection. So this one would be an AR, since that's on the air side. That's like the case we had over here. So you just tack an R on to the AR. And then when you go in, down in here, you're going from air to glass. So this would be here an T. That'd be like the regular T going in there like that. Oh, ART, sorry, ART. My mistake there. So that would be going from AR into here. You would just hit the AR with the T transmission. So AR with the T transmission, AR with the R for reflection. It takes care of this one. And then the AT bounce back, ATR prime, because you're reflecting now from the glass side. And then here, to get the one last one we haven't checked off, this one up here would be AT T prime. Okay, now here's where the fun begins, because now you know that this A here has to be AT T prime plus the ARR. All right, since there's expressing this in two ways, as the A and then as the sum of these two. And then this one here, this is expressed as two ways. It's going to be 0, so it's 0, but it's also expressed as ART plus ATR prime. Now this one immediately gives us, since the T's are going to cancel out and the A's are going to cancel out, this one immediately gives us R prime is minus R. That is a very cool result. And that kind of makes sense from the point of view that if you go from, let's say, when you have reflection, like if you have a rope like this and you hit a brick wall, then it reflects back with the flip. You know, it flips over. But if you were to go here to another string, which had a less density, it would not flip on the reflection. So here, when you go from air to glass, that's like a hard reflection. That's going to flip compared to the one going the other way from glass to air. Won't have that phase change. So anyway, this is very elegant, because without getting complicated into strings and all that stuff, just by looking at this, you already have the result. R prime is minus R. And then what else can we say? Well, from this one up here, all the A's cancel. These A's cancel. So you have, in this case, you have 1 is equal to T prime plus R squared. So when the A's cancel, you have 1 here, 1 and 1. So 1 equals T prime plus R squared. And that's a cool relationship. You see, that's saying T prime plus R squared. I think I'll just write it like this. The reflection one first plus the T prime is equal to 1. So there are two guiding equations. And notice that T does not equal T prime. If the T were equal to T prime, then you would have R squared. So therefore, R squared plus T squared is not equal to 1. All right. And we did look at that earlier, where we found there was a little tricky thing going on in the earlier chapter when we were looking at that. So this is very, very simple. That keeps you out of trouble with these results. So that is Stokes. So let's look at Stokes. Here is Stokes, Sir George Stokes, 1st Baronet. And he's known mainly for his Stokes theorem in vector calculus, which can then be used to derive two of the differential forms of the Maxwell equations, two Maxwell's equations in differential form. And the other two are put into differential form using the divergence theorem, also called Gauss's theorem. And we actually did that. That's the one we did do. We did 2 of them. Okay, so now we're going to apply this x3, and that's going to be multiple beam interference. Now for multiple beam interference, what we're going to do is consider a slab, like just say glass or something like this, and we're going to send in a beam like this, and this beam is going to have some reflection and some transmission. Now I'm not going to do any refraction here, because we're going to be looking at small angles anyway, so let's just go ahead and draw that like this, go in like this, and that'll continue through like that, and this will then like bounce back like this, you know, bounce back like this. So and this will continue on like that. So if this is, say, E naught, like that, then we're going to go from air to glass, and this is air. So air to glass, remember, when you go from air to glass, if we have a little inset here to just remind us the rules, if you're going from air to glass, that this one here, like if this is A naught, this is going to be A naught times T, and this one's going to be A naught times R. But if you're on the inside, say some B naught, and you're going to go out, out this way, then it's going to be B naught T prime, and then for the reflection, it'll be B naught minus R, because remember that this is the R prime, which we have from earlier. And then you can stick a lens on here if you want to focus the light at some point, P. All right, so just look at these. This one here is a transmission on the E naught, so you just slap a T on there. And then here, since we're leaving the glass, this is E naught T prime. Now this one on reflection, since you're on the glass side, internally you're reflecting, this has to have then the minus R. So this is going to be minus E naught TR, for this one. And then the one that's going out here, this one here is easy. This is E naught R. And then this one just simply hit a transmission on this one. And what's that transmission? If you're going from glass to air, it's a T prime. So this is minus E naught TR T prime. Okay, then we have here, this is another reflection internally. So this is a minus, R kicks in again. So that'll be then 2 minus R as its factor is going to be R squared. And then when you come out like this, you just hit this with a T prime since we're leaving the glass. This one here is going to have another minus R, so this is a minus E naught T R cubed. And this one, you're going to have whatever this is, minus E naught T R cubed, just slap a T prime on there. This one's going to have another minus R, so this is going to be E naught T R to the fourth. And then this is going to be E naught T R to the fourth, and you slap the T prime on there. So let's check them. Here you have E naught coming in, you have E naught R going out, and E naught T going in this way. Let's do all the reflections internally. Minus R on the E naught T. Minus R again gives you E naught TR squared. Minus R again gives you then minus E naught TR cubed. Minus R again makes it a plus R to the fourth. So the E naught T stays the same, but you simply pick up a minus R quantity squared is going to be a plus R squared. And then if you hit it with a minus R again, you have minus R cubed. Hit it with minus R again, you get R to the fourth. Then to get these, all you have to do is take this one and put a T prime on there. You take this one and put a T prime on there. You take this one and put a T prime on there. Now, I'm not really concerned about these as much because I want to do the transmission case, but let's just look at these. E naught times the R. This one is going to be whatever is down here and smack a T prime on the far right. This one's going to be whatever is here and smack a T prime on the far right. Now, I'm going to be interested in the transmission one, but before I do that, let me just point out that there's going to be a phase change, because remember our KX rule for the phase, how it's going to evolve if we go a distance. And remember, this is K naught N times X. And here, this X, when we have angles that are very small, this is going to be a distance D, and we're going to be doing here, we're looking at, let's do for round, a single round trip. So a single round trip from here to there, and then that's a round trip, see, and then there to there, like that. So if you're doing that, then you're going to have, for the phase, K naught N times 2D. And let's just call that, by definition, delta naught. Now here's why we're going to be using this. If we look at this one, and we want to compare with this one that's going out like this one has a round trip that needs to be added to get that one. So that's going to introduce the phase e to the I delta naught, all right? Because that's going to be the phase, and it's going to be affected there. And this one here is going to have then multiply it again. So this one's going to have here e to the 2 I delta naught, and going up and so on. So that little extra phase needs to be put into the analysis. So then we have, for the transmission, we have E naught TT prime, this first one, and then we're going to add the second one with the phase, and that's going to be E naught T R squared T prime with the phase tacked on there. And then this next one up here is going to be an E naught T with the R fourth in the middle, T prime on the end, and then E to the, this is going to be 2 I, 2 round trips in there. Here's a 1 round trip, and there's the other round trip that's going to be kicked in there. And then we go plus dot dot dot. There's a picture in a book here I have for you where I have one more, drawn. So you can refer to the book, has a more accurate drawing than the hand drawing one. But I like to hand draw everything, as you know, and show you everything as we go. All right, so that means this one, if we look at ET, we can pull out the E naught TT prime, and we'll have 1, that's this first term. And then here we're going to have the R squared with the exponential term. And here we're going to have R to the 4th, which I'd rather write as R squared, the exponential term, and have it squared. And then the next one would be R squared, the exponential term, with the cube to get the R to the 6th power, and so on, all the way out. Now we've seen something like this before. Remember when we had the sum of 1 plus, I'm not going to use R, I'm going to use X now because I already used an R, but we looked at this earlier using R, as we had this progression, geometric progression, where you multiply at each stage. And then here, rather than look up the answer, it's just as easy to just derive it. So if you multiply by X, you have an X here, then you'll have an X squared, and X cubed, and the last one will be X to the N plus 1. And then what you do is you subtract, and if I subtract here, I'm going to subtract the bottom one from the top one, then this cancels, and I'm left with a 1 and minus X to the N plus 1. And then I can factor out 1 minus X there, and I get the famous formula, 1 minus X to the N plus 1 over 1 minus X. So that's a formula. I don't bother memorizing this, because I can derive it like in 30 seconds or so, faster than I can look it up. So then what we do here, we notice that this R is coefficients less than 1. So since that's less than 1, when you have less than 1 case, watch this. If you take the limit as n goes to infinity, and since the x is going to be less than 1, then this fraction to the infinite power is going to be 0. So you get 1 over 1 minus x. Now you might worry and say, well, but wait a minute. You got this exponential in there. Aren't you worried about this exponential? Well, yeah, we should worry about things like that. It's all right. So let's do that. If we look at this here, we're looking at, say, you want to look at this term where you have this is your x. All right, so we said before, if n goes to infinity, like this, then if you raise this to the nth power, x to the n plus 1, what's going to happen there? So let's do it. So if you go from n goes to infinity, and you have r squared e to the I delta naught to the n plus 1 power. So nice thing here, what we can do is bring that n in there. This is r squared to the n plus 1 power, and this is then e to the I delta naught n plus 1 power. And then when you take the limits, we're going to use that property of limits where we'll take, when we have the product, we'll do this one here, and then we'll have the second factor over here, taking the limits. And you can see that these are sines and cosines. This is going to be like the cosine of delta naught n plus 1 and plus the I sine of delta naught n plus 1. And as n goes to infinity, these things keep, when n's large and large, these things keep wiggling. But the neat thing about them is that if you look at this, they're bounded by 1. In other words, this thing here, like if the cosine is 1, all right, then you can get 1, but sines and cosines never go more than 1, so that's bounded. This is finite, and this thing's going to go off to, when it goes off the thing, it's going to be 0, so it still works. It's not a problem. Okay, so then what we're going to do is replace it. So we come up to here, we know what the x is. The x here is the r squared e to the I delta naught. So that gets squared and that gets cubed. So that's the x. And that's what's going to go in here. So when the limit, the limit of this thing, I probably should write that out a little cleaner. The limit as n goes to infinity of Sn is equal to 1 over 1 minus x. There, that's what I meant by that shorthand notation. So that means this gets put in there, but remember this has to go in the front. All right, so we need to have this also in the front because that's part of we're going to put that in front of the s, it goes in front here. So that means what we get for ET is E naught TT prime, and then 1 over 1 minus, and here comes the x, the r squared e to the I delta naught. Okay, that's the formula. We're going to use the fact that TT prime is equal to 1 minus r squared. But remember, the actual reflection is given by r squared. So the coefficient of reflection, to get the reflectance, all right? So the reflectance is this parameter r. So here, we're going to write this as 1 minus r. And then this r squared is simply r. So that means for the transmission, we're going to have the E naught 1 minus big R over 1 minus big R e to the I delta naught. That's where we stand. The next step is to find the irradiance of the transmitted light, and that's going to be 1/2, take the modulus and square it. So that would be 1/2, and we can do that by taking the E naught and then take the same thing with the star. So that's if you have the Z is A plus BI, to get the Z, this squared, you can just say Z star, where you go A plus BI, A minus BI, and that's a cool way to get A squared plus B squared. So this is E naught, 1 minus R over 1 minus R e to the I delta naught, and that's a star. So what the star is going to do is go in here and make that I, wherever there's an I, you're going to flip it to a minus sign. Now there's a lot of stuff to write down. I don't want to write everything down, so I'm going to call the numerator 1/2 E naught squared 1 minus R squared. So I took this here with the 1/2, all of that, and since the star on something real doesn't change it, like that's the A. So this is the A. And then what we'll do is we'll take this down in here, and we have to make sure we keep the star. We'll call that a D for denominator. So the denominator is then 1 minus R e to the I delta naught, 1 minus R e to the minus I delta naught, because that's when the star operates in there, the I has to change to negative I. So what is this? This is 1 minus R times the quantity e to the I delta naught plus e to the minus I delta naught plus R squared. Let's check this. 1 times 1 is 1. 1 of these with the negative and 1 of these with the positive gets you this. So you have the minus. In other words, this is minus R with the positive when this hits it. In fact, we'll do it like this. This one's going to go with this, and this one's going to go with that for the cross terms, So in either case, you have a minus R and a minus R. So put the minus R there. And then I just simply add these two cases. The last one, 2 minus signs going to cancel. R is going to go squared. And then if you multiply these two, you're going to get 1. Since e to the I alpha times e to the minus I alpha is e to the 0, which is 1. So you get this. Notice, by the way, that this is 2 times the cosine of delta naught using the Euler formulas, which are very, very important. And those I do memorize since they need to be used quite often. This is minus 2R cosine delta naught plus R squared. And now I'm going to do a little manipulation here by subtracting R, 2R, and I'm going to add 2R and rearrange the terms slightly. So here I have this 1 there. I put in a minus 2R, and I'll have to add 2R somewhere. Then I put this R squared here, and then this one came over to there. So once when I have this, I'm going to now notice that this is 1 minus R quantity squared. So, if I square this, I have 1, cross terms minus 2R, and then plus R squared. And then over here, I have this cool factoring. I can factor out the 2R and get this nice result. Now at this point, most books will just go ahead and look up the trig identity to replace this. So I'm going to remind you of what that is and review for you a little bit of the Euler manipulation. So I'm going to review for you that this, I'm going to show you that this is 2 sine squared delta over 2. So you can look up that trigonometric identity very few people actually memorize that. But I want to just show you that and just review a little bit for you why that works. All right. And sometimes they'll give this a sign with a theta. And then if you do that, then this is a 2 theta. So there's like different ways of looking at this. So if I look at this subtraction, this is 1 minus e to the I delta naught over 2 minus e to the minus I delta naught over 2. Remember, for the cosine one, you add these together, they have the same sign. So this is subtracting. This is your cosine of delta naught, say is e to the I delta naught plus e to the minus I delta naught over 2. And so here we're subtracting these two. So if we do that, now watch this trick. This is 1/2. Since I know I need to get this, here I'm sort of showing you here the formula that will bring us there. All right, so we do this. Okay, so we have this. Let's check this. If you were to square this first one and put a minus sign there. If you were to square this first one, you would then get here this term. If you were to square this second one, you'd have the minus 1/2 there. And when you square that, this will become a plus sign and you'll double up on the exponent, but still have a minus sign. Don't get that one. And then the cross term would be, when you multiply these together, you're gonna get e to the 0 power, and it's gonna be a negative, so it's a -1, but there's 2 of them because remember cross terms have that 2. -2 will cancel -1/2, and you get this. So once we have that, I'm going to stick down in here. What I would like to do is stick the 2i down on the bottom. Since whenever I see a minus sign and these exponentials like this, with a plus and a minus like this, then I would like to have a 2i down there because that's going to give me the sign squared. But if I put a 2i down there squared, I need to put a 2i up here squared. And remember, there is a minus 1/2 out here in front. So now if I do this, it's going to be 4 minus 4, because the I squared pops out as -1 over -2. So this will be a +2. So that +2 is this 2. And this sine squared is this one. So we just showed this identity. No big deal. Just a review of manipulations with these exponentials. You did prove a few things for homework, and we did some for in class. I just wanted to review that for you. Okay, so now that means what we have is we can replace this D equation here is 1 minus R quantity squared, and then plus we're going to have here this 2R is going to be there, but that's going to hit this 2 to make this 4R, and then this sine squared of delta naught over 2 goes for the ride, right, with us. Now we take that and we take the A. So we need to divide the A by this because the A was our numerator, and we're going to divide. Okay, here are the 3 equations we have looked at. We have looked at the irradiance of the transmission, and we have a numerator, and we have ourselves a denominator. Now for this denominator, I want to introduce the coefficient of finesse. And the coefficient of finesse is defined in a way that we pull out the 1 minus R quantity squared. Then we have 1 plus 4R over 1 minus R quantity squared. And the reason why we're doing that is because we want to cancel. We're going to be dividing A by D, and that's going to cancel. And this part here is called the coefficient of finesse. This part right in there. So F is 4R over 1 minus R quantity squared, coefficient of finesse. And when we do that, we're ready to now do the irradiance. We want to take the A and divide by the D. So the A is 1/2 E naught squared, 1 minus R quantity squared, and then divide by the D. The D is, see, we had pulled that out. That's going to be nice. That's going to cancel in a second. And then we have 1 plus F times the sine squared delta over 2. Nice result. This is going to cancel. And then we have for the irradiance. And at this point, let's group all the constants and call it, say, I naught. So this is a clean that 1 plus F over sine squared delta naught over 2. So this is our final result. And if you want the reflection, the radiance of the reflection by conservation of energy, that will be then I naught minus the transmission. If you sketch something like this out, you find that when this denominator goes to 0, you're going to get yourself a peak, because this is going to be, up here, I naught is going to be maxed out. This is your I, say, and we're looking here at the different cases of delta. So we want to figure out here, like, when these max are going to occur. Well, you want the sign to be 0, so you'll get your max, because if you have 1 plus something, you're dividing by something bigger, you can get something less than I naught. And then here, if you want that to occur, you want this phase to be some n times pi. And that will definitely, do the trick, where n is like 1, and then 2, and, 3, and on so. Here, remember, for the normal instance is what we're doing. We're looking at here the delta for normal incidence, K naught, and 2D, n's index of refraction there. So this will occur. So the thing I want to really point out is that when this F gets bigger and bigger, that means you're going to basically be on the low end here, unless you're right at the place where this so happens to conspire to get you 0 and kills the F, then you're going to get there. So if F is very, very large, that means when this is getting close to F, the large number will be a large number. One of our large numbers will be 0. So in other words, this helps us understand this kind of a situation, versus this kind of a situation. So here, if the F is very, very large, that means you're going to have 1 over something large usually. So usually you're going to be near 0. But then when the F gets killed, all of a sudden, boom, you're up there with this I naught. So that's what the finesse means. If the finesse is large, you have more resolution. If the F is not large, you get this. So to help get a rating on what this is, more specifically, what we do is we like to look at what it is. You have the full width at half maximum. So say like 50% of the way up here and here, say. You take your belt size, and that's going to be the full width at half maximum. Like this is like 50% of the way to the top. And that's going to be an x1, say, and some x2. So we solve for that by taking our equation, and we want this denominator to be 2 to get the halfway mark. So if that's the case, you want the F sine squared delta naught over 2 to be 1. In other words, you want the sine squared delta naught over 2 to be 1 over F, and you want the sine of delta naught over 2 to be 1 over the square root of F with a plus or a minus sign, like that. So since we're at the normal incidence, this is basically the same, sine of an angle is the same as the angle, and that's then plus or minus 1 over square root of f. So this delta would be approximately plus or minus 2 over the square root of f. And that means we can identify the x2 as the plus 1 and the x1 as the minus 1, the plus or minus 2 over square root f. And then if you want to subtract them, then you get the full width at half maximum. You can think of that as the full diameter of my waist. Say if my waist is like halfway to my head, or the height, half my height, I want the full width, like the waist diameter at the halfway point. So it's the waist. This is the waist diameter. So if you do that, you then get, when you subtract them, you get 4 over the square root of f. Now, in some books, they'll go more and define the script finesse as 2 pi. We're not going to be using this really, but I just wanted to introduce it, this definition. And then if you take this definition, you have then 2 pi over this thing, 4 over the square root of f, and that's then pi square root of f over 2. And that will appear in one of our graphs that I show you. And just one last final thing, notice that this definition that we had here with the k naught n 2d, you can always replace this k naught with 2 pi over lambda naught. And if you do that, then you get 4, 2 times 2, and then you get the pi and the n and the d over the lambda naught. That formula there can be useful at times. Okay, so let's look at what we got here. This is the main thing I wanted to show you, that the tall and narrow type of a peak occurs when the finesse coefficient is large. In this case, is 10 down here. The coefficient of finesse, the script one, is 10, and then here it's 2. So this is more spectral resolution when you apply this and try to make a measurement of a wavelength. This is good, this high finesse. So that's some of the basic physics that goes behind certain things with spectroscopy and interferometer work. And now we go to some examples of applications. Some examples of applications. The Fabry-Perot interferometer here works on this principle where you have two devices that can reflect back and forth. There's an optical path difference, and here with the high finesse values, you get nice sharp rings when you have interference interference effects. And here, this is the effect where the finesse is not so large. So this is one of the applications. It's a very important application in spectroscopy, the Fabry-Perot interferometer. It's very nice. And that's here, if we're following our X's, I call that X4, which is a short mention in the book. And then we go to X5, which is a discussion on lasers, because see, the laser principle is going to use two reflecting ideas with an optical path difference, in the middle. And this back and forth is going to bring into existence a stimulated emission of radiation that is very, very intense and amplified, and that's the laser. Laser goes back to Einstein. So Einstein suggested that if you had, say, a system where we're going to do a little diagram here like you do in chemistry, where this is the excited energy, higher energy level, and this is say a lower energy level like this, that if there's something up in this state, in the higher state, and it's say metastable, which means it easily can come down, but it's there, it's staying there for a little bit. And then if you come in here with a wave that has the right frequency, it can yank this down. And then what happens is you get two waves that are traveling together. And here's the concept that Einstein taught us, that light consists of photons. So you can think of a photon coming in, yanking down, let's say a transition to make another photon. And since these are in step, we call that coherence, where the light is in step. The crest, each crest, trough, each trough, that's coherent light, light's in coherence. So Einstein made this suggestion or idea in 1917, and it took a few decades for it actually to be realized. But this idea of bringing down these, so you have to pump these up to get them in a higher state. Then when you send in the lights, just bring them all down together, and that's going to be the definition of the laser, which is the light amplification by stimulated emission of radiation. So in other words, by yanking down these electrons, you're stimulating the emission of the radiation, because when an electron goes from the higher to lower, it's going to shake off a photon, and that's going to then be with the other photon together, and then a cascade. It'd be like more and more happening, like a chain reaction kind of effect. You can just think of all these electrons up here, and then as the photon comes in, it yanks this one down. Now we have 2. Yank that one down. Now we have 3 in step. Then we have 4 in step. And then the mirrors are important, so let it go back and forth and get lots and lots. And then a little opening in the mirror, or perhaps maybe a half silvered part there, that lets some escape out of the system. So let's look at this in a little more detail with some of these diagrams. So here's the excited level before emission, and then this electron is going to drop down to this state, giving off a photon, but this photon is going to stimulate it. It's going to, in a sense, yank it down. When it says wiggling like this, yank it down, and then you're going to have 2. You're going to have the initial photon here, and then the one that you brought down with it, and they're in step, and that is coherent light. So that's the basic idea of the laser. And then in this next diagram here, we have then the principle of the 2 reflecting surfaces, which is like a principle that we've talked about, at the beginning of our class, the 2 things that reflect. So the laser is using this, their separation now is quite large. And here you have some lasing material which can be put up in that excited state that's metastable. And to do that, we need to have some pumping energy, some energy to do that, to get the electrons up. And then we're gonna, then what'll happen is, if one comes down on its own, which it will, then when the light travels, it'll bring another one down, you get then sort of that chain reaction effect. And this is the left reflector and the right reflector back and forth with a little, say, maybe half silvered or something there, so that the light can escape, but it needs to be sealed off. You don't want the gas, the laser material to escape. So then the light then goes off. That's your laser beam. And we go back to the beginning of our class. Well, we had laser beams here now that are quite inexpensive. You can use them as pointers, very, very cheap. Amazing invention, the laser being realized as a little pen sort of pointer. Here's another schematic, the classic helium neon laser, where you have helium neon gas reservoir, and you're going to then use that to get the lasing effect. And here is a little more detailed diagram of what's going on. You got the helium neon, you got the excitation by electron collisions. So the collision, say, is talking about collisions between the helium neon collisions, getting the energy to get up there. And you plug this thing in, get electrical energy to get this thing started, or you have with the little laser, you have a battery in there. So this is the classic helium neon laser, and then the transition that gives you that beautiful red, which we're all familiar with, and you've seen a lot of homework problems, 632.8 nanometers, the 633 nanometers, red light, is coming from this transition, and here they're putting in some chemistry detail into 5S, here the 3P. In chemistry, we learn about these energy levels, and that's going to be the one that's going to be the lasing one, where this transition come down there, shake off the photon that has the 633, and this is what it looked like. And we have some at UNCA. These go back many, many years, and I remember when I was a graduate student, I was working with Dr. David Falk as a teaching assistant, and this is amazing. It was like in the mid-1970s, this guy used this, grabbed this from a lab, and used it as a laser pointer. So this is back like in the mid-1970s, using a big laboratory, laser as a pointer. He had the idea. First time I've seen that, and now of course everyone does it now with the little pen light, laser units that you can point at the PowerPoint in class. This is what we had when I went to school. This is Dr. Falk's laser, back in the old days. In fact, this one may not even work anymore. This is so old. Let's see. Look at that thing. This was it. Now, I have to give Dr. Falk credit. Now, he's the guy that you saw there. He had this way back in the 70s. He brought to class. He got it from a lab, all right? And he used it as a pointer. I mean, literally, he was using it. I mean, he was doing it. I mean, the guy. And this one here has a flaky fuse. This has a fuse back here, so this is a little erratic. But I wanted to show you this one. Right? Yeah, it's falling apart. Yeah, we put the fuse in there. It sometimes comes out. But it's nostalgic. It goes back like 45 years or so, and that's the old laser. I like this diagram here, which shows you the monochromatic nature of the light. This is the spectrum of the laser light. So this is the 632.8 nanometers, and see, like the light is basically like zero here. It's like like I said, background noise is this is zero. Let's say if you're like in a room or something, and then boom, you get this. So in this kind of a diagram, you gotta be very careful. You never look at a laser beam. Laser can damage your eye. So here, this is done electronically, a measurement that's made. It shows you that here, like background noise and the measurement very, very low, and all of a sudden, boom, this tremendous intensity of the light at the 632.8 nanometers. This is your 600 here. This is 650. This is your visible spectrum at 400, and going here from 400 to 700, and the spectrum for the laser beam, a spike. Amazing, look at that. Next shows a discharge going on in the picture. So this is a discharge. The glow is due to electric discharge, and the laser spot is over here on the screen, and it looks a little bit white because of oversaturation occurred like in the camera taking the picture. So that's nice. And here, beautiful example of commercial lasers here. This top one here at the 660 nanometers. This one here at 635, and then 532, 520, we're in the green, 445 in the blue, and 405 in the violet. Very, very nice. Very, very impressive. One final comment on a personal note is Charles Townes, who won the Nobel Prize involving the laser, and I got to meet him. He came to Asheville because his sister lived in Givens Estates, nearby UNCA's Asheville area, and his sister invited me and physics folks to go watch his talk, and he gave a talk at Givens Estates, and he gave a talk the next day at the church at First Baptist in Asheville, and he talked about the astronomy, and he talked about the religion and science, but he didn't talk about lasers. And he is also dear to our hearts here in Asheville because he grew up nearby, and he went to Furman, which is in South Carolina, only about an hour away from UNC Asheville. And he got a bachelor's degree in physics and in modern language, got a BA, got 2 degrees from Furman, and then a master's at Duke, which is in North Carolina, down the road from us here, about 4 hours or so, in Durham, North Carolina, and then off to Caltech, and a Nobel Prize in 1964. He shared the Nobel Prize. So when he came and visited in 1995, it was about, and he at that point was 80 years old. He lived to 99 and a half, died in 2015. So finally at this talk, someone said, look, tell us what the laser is. Like, tell us about the laser. See, because he basically worked with the microwave, the maser. That's a microwave amplification by stimulated emission of radiation. In 1951, he invented a device to work in the microwave region. So he said, he was wearing a black suit, like this one here, and he held out his arm and he said, if it's black, you're going to absorb. So imagine having something that when you shine light on, it gets brighter and brighter. And that's what the laser is, and that's how he was explaining this amplification process to the layperson, how that the light gets brighter and brighter. By pumping up electrons, pump them up in a certain material, you pump them up, and they hang out there for a while, and then when one that comes down, it'll then send out light beam, yank the other one down, kind of like a resonance phenomenon. And it's our Charles Towns from Furman down the street, who died, by the way, just recently. He died almost at age 100. See, 1915, when he was born? This is amazing. So Towns, there he is. Towns from South Carolina. He visits his sister in North Carolina in 1995 at Gibbons Estates, a retirement community. And her sister writes the physics department. I was chair at the time. And says, hey, like my brother's coming, like Charles Towns, y'all want to come and watch him talk? And I'm going, whoa, the inventor of the laser? We definitely, let's go, kids, we're all gone. I take the family, man. We're all going down there, And I told everybody in physics and all that, So we're all going down there. And he's at First Baptist Church the next day. He's doing another talk. He's doing 2 talks. So the one talk's on astronomy. And we're thinking, this is good. I like astronomy. But, why don't you talk about the laser? And then next day, maybe talk about the laser next day. So we go to the next day is Sunday, it's church services, and he's doing something there about religion and science. So finally one guy raises his hand and says, could you say something about the laser? Right. So finally he says something about the laser, and he had black on, right? He's wearing black, and he says, okay, like this black coat. He says, if you shine light on a coat, all right, you shine light there, say it's black, right, because it absorbs the light. Suppose you had a certain material, when you shined it, got brighter and brighter and brighter. So he's explaining this real cool. This is the way he's explaining this. Because here's you shine light, and this one got double light, got triple light. See? So that's kind of a neat way. That's like from the words of the inventor himself. All right, because I remember him putting that arm out, so dramatic. He says you just shine there, and you get brighter and brighter and brighter. Now you have to have a way to pump the electrons back up to keep the laser going. All right, but that was kind of neat the way he explained that. Just shine something and get brighter. And that's kind of the basic idea. Very nice. Charles Towns, and he passed away in 2015, just shy of his 100th birthday. That is a super neat connection. So he's from our neck of the woods down South Carolina, and went to Furman, and then went to Duke. See, Furman, Duke, and then off to California, Caltech. Nice. And his work was on the microwave, in the microwave. So the microwave is a similar idea. Light is light, just a different frequency. And he is like, in history, like a major character and scientist for the laser. And he got the Nobel Prize, for his work on the maser, which is the microwave equivalent, microwave amplification of stimulated emission of radiation. So that's neat. So it's kind of cool. Fond memories of that encounter with the Nobel laureate. He amazed me because then he was 80. And I'm going like, this is awesome. The guy's still like doing research. Like he was still doing stuff with students, and he's giving like talks, you know. And then he lived 20 more years until 2015, like almost 100. Hey, Charles Down.